Now that we demonstrated how well we are in dealing with presentations, let me see if we talk to you about how we can design robotic systems for performing more complex tasks. So I'm going to talk about my research, and I'm very happy to be here today. I like to solve the algorithmic problems for path planning and exploration tasks that are being deployed on the real field robotics systems that are actually designed for solving environmental problems. With that, so why environmental problems? Why we are interested in this? We all are concerned about the state of the world where the climate change is happening, right? One of the things that we can all observe are actually harmful algae blooms. And that's also particularly large problem down here in Florida. These algae blooms can not only hurt the biodiversity of the systems of the lakes or oceans that they are blooming in, but also the cause a lot of health problems for even the respiratory problems. Another devastating problem that we are seeing right now is actually devastation of the wild oyster reefs. As you might know, the oysters are natural filters for the sea, oceans, and many other environments. And the rate that they are diminishing is caused by the non-sustainable ways that we are actually harvesting the systems. Is there any ways that we can actually have to solve this problem? And there are a lot of governmental initiatives to actually promote science and engineering solutions to help to tackle this problem. Then we have a lot of wildfires that are happening, and we have these aerial vehicles that are commonly used in different applications, but how we can actually use them to early on detect the area sites that some wildfires are potentially going to happen. So. And finally, one of the fun things to do with the where you are living very close to the oceans is actually go and explore underwater shipwrecks or sunken objects. There are very large touristic sites around the world that they are just designed just to attract tourists for doing the underwater ship exploration. And one of the things interesting for us was how we can actually build maybe street view for the shipwrecks. Now, hopefully I motivated why the environmental problems are interesting and why are we interested also from the robotics perspective? Well, for one, the technical challenges in this field when we are looking into unstructured environments, which are the environments that this type of problems are occurring, are very hard to solve environmental planning problems. Or when we go to large-scale operation, especially when we move forward towards including also multiple robots or heterogeneous systems, the problem becomes more computationally complex and also it's known to be exponentially hard problem. Then, if we go down to the underwater world, that's another challenge that is opening up to us. We have the visibility, the color visibility, the color flows. We have visibility differences and different dynamics that we have to handle. But even without going into underwater world, we still have dynamic changes that are happening around us. Even on the surface of the lakes or rivers, we still have environmental factors that are affecting the motion or plan of our robots that we are deploying in the real world. That can also cause these, for example, stochastic energy consumptions for the robots that we have, like aerial drones. So with that said, this research, my research that I'm looking into can be, or planning and exploration problem can be characterized with these three dimensions. On one hand, we have the environment, depending on if we have information about the environment, or it's partially known information, or we have completely unknown environment, the spectrum will be different. Then we have robotic systems. We are looking at the problem from the perspective single robot, multiple robot, one-on-one heterogeneity, or multi-robot, or full heterogeneity. And of course, real world entails that we are dealing with the actual uncertainties. Those uncertainties can be controlled, or they can have only single source, meaning that we have only one uncertainty, such as, for example, energy consumption, or maybe we have uncertainty about the camera readings that we are receiving. And we might have multiple sources for that. The uncertainties that I mentioned can be the collection that we're looking into. So during my PhD, I have addressed the problem for known environments and partially known environments with single multiple robots. Particularly, I have defined the problem of exploring the environment as a coverage path planning problem, where the coverage path planning is to visit every single point in the environment, or as a problem of visiting the interest regions in the environment. Moving forward during my postdoc, I'm extending on the work that I have done for the single robots and partial environments. And I started working also with heterogeneous systems, where I'm using air and ground vehicles and also trying to move towards surface and underwater vehicles, where we also take into account only single source of uncertainties. So hopefully I've motivated why this problem is interesting and that it's worth to study this. With that said, just to give you an overview of what we're going to talk about, I'll talk about two particular research projects that I have worked, the multi-robot coverage and underwater coverage. And in between them, I will also show you how we can handle some uncertainties through the example of some of the projects that I have been working on. And these are just the top of the iceberg. At the end of the talk, we will talk about what is the larger vision for me and where I'm moving forward with my research. So with that said, let's start with the multi-robot coverage problem. So what is multi-robot coverage problem? One of the things that we want to do, for example, if we're doing the algae bloom study, right, we have to have some autonomous systems that go perform systematic monitoring or sampling of the environment, collect some data and return us some information about it. So that means that we want to visit maybe every single point of the environment to collect the systematic data about the environment. And the boats that we use usually, they are non-holonomic systems. What does that mean? That means that they have some minimum turning radius, and these vehicles are usually called Dubin's vehicle. They have Dubin's turning constraint. So given that, we want to solve the problem. Given a satellite map representation of the environment, assuming there is no communication between boats, there is number of the agents given and the minimum turning radius, how we can find complete coverage path that has equal operational time for each of these robots, the minimum overlapping area, we're minimizing the overlapping area, and also at the same time, we minimize the maximum trajectory cost per robot. The reason we want to solve the max problem is because we don't want to have a situation that we're minimizing the total cost, which can result in a case that a single robot might be performing the entire coverage expedition while other robots are waiting for them to finish up. So the first algorithm that we propose in this work is this high-level global path planning algorithm that tells robot which locations to visit. And the first algorithm has the following idea. Let's assume we have an optimal or efficient algorithm for solving for a single robot the trajectory, right? What we can do, maybe we can find the trajectory for a single robot and then split that trajectory into these multiple robots, right? So we can assign them parts of this path. So that's exactly what this algorithm does. So going into details of this, what it does, the first part of the algorithm is called Dubin's coverage solver, where it applies Booth-Joffredon decomposition problem. It generates path graph and solves generalized traveling salesman problem. So BCD is an algorithm, or Booth-Joffredon decomposition algorithm is the following. Given an environment representation, it splits environment into regions that do not contain any obstacles. So now it is a set of different cells that do not contain any obstacles. The path generation performs the following. For each of these cells that do not contain any obstacles, it will split areas into the splits that have the width equal to the sensor footprint. The path means that if the robot moves along this path, it will cover completely this single strip. So if we didn't have actually the Dubin's constraint, at this point, we can say that one way that we can do the coverage of this environment, just go over these passes, no matter which direction we're moving, right? But because we have the Dubin's constraint, it's important to know where we are doing the turns. It might be that going to the right next to its closest pass, it's actually going to result in much larger turning radius, and thus it will maximize the cost that we have. So for that, what we are doing, we are defining generalized traveling salesman problem, where the generalized traveling salesman problem says that instead of vertices, let me just first give you a definition of what is traveling salesman problem. If we have areas to visit, in this case, those are the passes that we have to visit, right? The problem is how we can find a path that visits all of these passes in the shortest time, and also visit them only once, or at least once. Generalized traveling salesman says that instead of single vertex, we have set of vertices. And now the problem is to visit this set of vertices, from which only one single vertex will be visited. So with that, if we have this path generation, now what we can do for each of the paths, we can assign what are the directions that we have to move. It's either up or down direction, right? So this is our vertex set for the generalized traveling salesman problem. Now, the cost of the edges between these vertices are going to be defined as the cost of the Dubin's curve plus the distance to cover the one pass, depending on the direction that we're going. Okay, so we got the generalized traveling salesman instance. Now we can solve single robot path planning algorithm using the GTSB problem. As a result, we are getting Hamiltonian tour. Hamiltonian tour is a tour that contains all of these passes in the most optimal routing configuration. Having the Hamiltonian cycle, given the number of the robots that we have, now the idea is that we have to split each of this region in an equal amount of the work to assign to each of these robots. The way we do it is through solving a clustering method. And the way that we define the cluster is to assign semi-equal regions for each of the robots to cover. The simplest way we're doing this in a greedy fashion will be, we know what is the size of the entire trajectory, right, which is the L. Then we can split that into, if the number of the robots is K, we can split it to K regions, right? So the paths, each of these regions will be dedicated to each of the robots. But we have to take into account also maximum distance that each robot has to visit to go from the start point to the locations that they have to visit. And that's where the S maximum comes into it. It finds in this original optimal trajectory what is the farthest or the most costly tour that it has actually taken in the worst case, and takes it into account into cost of the cluster. And then assigns to each of the robot corresponding section of the path that they have to traverse. And as a result of this, we have K routes from the original path, from original efficient path that are assigned now to each of the robots. And then we can generate waypoints according to that will be executed in the real world. Each of the colors of this picture represent the different regions that have been assigned to 4 robots. The second algorithm is Dubin's coverage with area clustering. So the difference between this and the first algorithm is that in the first one, we have generated first the path, optimal path, and then we assigned each of the paths corresponding region from the path, from the optimal path. But what we can do now, the idea in the second algorithm is that let's first split the environment into equal regions, and for each of these regions, solve the optimal routing problem. And that's exactly what we do here. We again do the Bootstrap-on decomposition, we do the path generation, but instead of solving the one single robot efficient path planning algorithm, now we create the dual graph. Dual graph is a graph where each of the vertex corresponds to the middle of these cells, and it connects only to its neighbors. And the neighborhood is defined as the closest regions that they have common edges. So on this dual graph, we'll perform some clusterization. The dual graph is going to be our skeleton for performing clusterization of our region. Having the dual graph, now what we can do, we can actually just do greedy type of clusterization where we're using breadth first search algorithm to split the regions into clusters. The cluster size here is defined a bit differently. Again, we are taking into account the distance that the robot has to travel, but also we are taking into account that every time that we cluster, but that we assign robot one region, now the total area that has been left to cover is different. So we can extract that size and assign the remaining of the cluster to the next robot.
So is this similar to GMCP, generalized minimum check problem?
It's different, but I think they can be reduced to the similar type of problem. But
So you are using greedy algorithm. You are not using like some linear programming or dynamic programming.
no, the reason that we didn't do the linear programming because this approximation method was giving more or less good results. So we used the heuristic. We came up with this heuristic method that was using that was solving multiple traveling salesman type of problems. But exactly, that's right. We can define it as a linear programming method.
Yeah, I mean, it may not be optimal.
Yeah.
Solution.
It's still not optimal because this is heuristic solution, right? Nothing that we are going to do here is going to be optimal. All of these problems are proved to be exponentially hard, which means they are NP hard problems. So that means that there is no exponential, there is no polynomial time solution for these problems. And usually when the problem is NP hard, the way that we approach it, we either come up with heuristic, in which case we cannot prove what is the approximation, or we give approximation algorithm that says how close we are to the actual optimal solution. But the solution that we are using, for example, when we apply the traveling salesman or generalized traveling salesman problem, we actually use some existing packages for the solver. So they usually will solve some heuristic or sometimes even exact solver, which are sometimes fast if we don't have very large state space.
Yeah, we have worked in the GMCP and we have a linear programming solution for the results. But this is not exactly GMCP.
Yeah, no. The version of this, the original one without Dubin's coverage, we can represent it as Chinese postman problem instead of a traveling salesman. And the Chinese postman problem, it's a polynomial time, has polynomial time solution, but for single robot again. The moment that we add even for Chinese postman multiple robots, it is proved to be NP hard problem. And as a result of that, so on this stage, we cluster each of these regions. Now we have equal, semi-equal regions that each of the robots can actually travel, can perform the coverage. And now what we do for each of these regions, we actually now solve the generalized traveling salesman problem that I showed on the previous stage, right? And as a result, we get this K number cycles that are corresponding to each of the robots. And they can be applied to deployed in the real world. What we did, we have compared the non-Dubin vehicle algorithms with some baselines where the baselines were chosen to be Nare route clustering, and also the original version of the FHK clustering method that I showed on the first slide. So the objectives that the metrics that we have calculated are the utilization, where the utilization means how many robots have been assigned a task, and maximum coverage cost. It showed that notice that maximum coverage has to be minimized, so lower is the better the value. And the utilization, it has been improved. That means that more robots have been actually assigned regions to perform the coverage. And we generated random obstacles maps that we have applied this algorithm for about 200 random images.
So how many robots are in this group? These results?
So this results is going to be shown on this example, how many we have used. We have used up to 32 robots for each of the experiments, and we have the comparison here. And it showed that the utilization in average for all of these examples have been increased by 20.5% and minimized the coverage cost of the maximum path by 39.8%. And this is again averaged over all of these experiments. We have executed that also on real maps, one from the rural Quebec environment and another one from the cave area. And these are different illustration of different algorithms visually to see the difference between the algorithms. One thing that you can actually notice that in the CAC algorithm, because we were using this dual graph and we were first splitting the environment is kind of, if you had a cake and you were just cutting like with the parallel lines, that's how the second algorithm is going to give you, because we are first splitting the environment in a greedy fashion, not a greedy, but BFS fashion, right? Greedy, BFS is still greedy, but it gives you an optimal solution. And here experimental comparison between these two environments, which are real. And again, we see that both are performing on the maximum area coverage, but we notice that CRC is performing better than other methods, where CAC is not giving that much improvement. With that, we compared also, we applied on these environments the CRC and the CAC algorithm on the small lake Murray map and large maps on the complete map, and rural Quebec that I showed in the previous. In this experiment, we had 5 and 10 robots corresponding respectively. These are the executions in the simulation, and one thing to notice here is that the circular areas that you see at the edges of the maps, those are the actual Dubin's turns that the robot has to perform. And sometimes you will notice that going to the right next to the closest path was not optimal, and robot had to actually take another route to minimize the route. Sorry, I think I missed the slides. Okay. Oh, this was visual, that's why it's not willing. I apologize for this. So these are the field trial examples. This is the slide that it was missing. So experimental setup has been consisting of this JETIAC boats that we have in our lab. We have built about 6 of them, from which 3 have been deployed for this experiment. We made them autonomous in the lab using the Pixel controller for wafer navigation or performing any type of navigation. We have Raspberry Pi that collects the data and records them on the board of the boat, and we had used single ping sonar to actually collect the bathymetric information of the environment. This boat actually can we can deploy different type of sensors on the sides, and they are very modular. So depending on the type of the sensor, if you have the mounting capability, you can actually put that on the boat. These are the example of the executions of the field trials we did with single, 2, and 3 robots. You can see here that one of the robots has very wonky trajectory, and this shows the challenges that we are facing when we are working with the real robot systems. All of these boats have exact same configuration. They have been tuned in the exact same way, but on the day of the trials, one of the boats, even though it was performed the same exact trajectory, but at the end of the day, we found out that the GPS information was not correct. On the experiments, we have used sensor footprint 4.5 meters, and also turning radius was set to 5 meters. The experiments here, for each of the experiments, we have spent about 1 to 3 hours time, and it has covered about 200 over 200 area on the lake Nare. So the contributions for the multi-robot coverage are as one. We have communication-less complete area coverage. We have compared CRC and CAC algorithms that have showed outperforming the baseline algorithms, maximizing the utilization and also minimizing the maximum cost. We have 2 heuristics that are taking into account the Dubin's vehicle constraint, and we have covered about 200 area.
So what is the Dubin curvature? Any information?
The Dubin's, the vehicles that we're using, they are non-holonomic, so which means that they have turning constraint. So if you think about two-wheeled vehicle, right? So the way that you can turn vehicle right in on its place, you can just turn each of the wheels in opposite direction, right? It actually can just turn on the same spot. But if you have a vehicle that has to actually travel some distance in order to be able to turn the heading on the same direction, that's called non-holonomic or Dubin, or a vehicle with a Dubin's constraint. So there is this minimum turning radius that vehicle is gonna take in order to perform the rotation.
So the particular curvature of Dubin.
Yes, and you can calculate that mathematically, depending on if you are starting from left and then turning to the left or left to right. There are different formulas that you can use that. That's what we use for defining the costs from edge to edge, from the vertex to vertex.
There's a proof that the optimal Dubin step trajectory is always straight lines and maximum curvature. So you will never go like from a nice smooth curve. You will go this way and then
Yeah, that was, I was noticing it was going only vertical.
Yeah, so they look like this. They alternate between straight lines and maximum curvature.
Yeah. Because I know the Gaussian and mean curvature, but these are newer.
Yes.
It's the principal curvatures and so on. The classical differential geometry. Yeah.
Yeah, and most of the vehicles that's we're probably dealing with, they're always going to have some sort of minimum turning radius. So taking that into account is probably important. Except if we're using the UAVs, you can turn any directions with UAVs. Yeah. So we had this high-level algorithm that I just showed you, right? So the result of that algorithm was waypoints. And we're assuming that going from one waypoint to another waypoint, nothing is going to happen. So our robot is going to be able to travel from one waypoint to another waypoint. But we're dealing with real world, and that's not actually true. So here is an example of that of trajectories that we have planned. We put the waypoints in the mission planners, and the yellow one is the actual trajectories that we wish that our robot will be performing. One of the reasons that we don't want to have this kind of situation is that if we're doing coverage, we don't want to have overlapping regions, right? So the executed trajectories had the look that is depicted here in the white. But how we can actually resolve this problem as well. So during my PhD, I worked with my colleague Jason Moulton to addressing this problem. One way that we did, we actually collected data with our bot for the external forces. So external forces in this case were water current and also wind speed. What we did, we thought about representing them as a Gaussian process. So if we have some representation about the environment, and when we are doing consistent monitoring of the environment, we can actually use these predictions for maybe next day to actually perform another navigation and tune our PID controller. And that's exactly what we did. Using this Gaussian information, we can actually perform the PID controller tuning, or we can also do supervised learning to understand what will be the difference between the waypoint that we have given and the resulting waypoint that the robot has traveled. And this way we can actually tune our controller. With that augmentation, you can see that in the first case, we have the controller without the tuning from our augmentation. And then in the yellow, you can see that when we are using the augmentation, using our predictions from the wind and the current, we were able to improve the trajectories better. And this can actually drastically help to not have any overlaps in the coverage method. So this is one way of doing the integrating the uncertainties into our system. Another way, another source of uncertainty might be energy consumption. Again, we have these nice waypoints. They are generated from the global map, from the global planners. If we have heterogeneous systems, for example, UGVs and UAVs, each of them have this coverage path that they have to travel, right? One uncertainty that we can take into account is the energy consumption of the UAV. We can use the UGVs to perform charging, recharging of the UAVs. And how we can do that? We have to find the rendezvous locations, right? So given that we have the routes for each of them, stochastic consumption, how we can find where and when the robots have to meet in order to minimize the failure of the system. The way that we did it, we have used the risk-aware planner to minimize the expected mission time subject to probability of mission failing to be more than a tolerance rate that has been defined by the user. And the way that we did it was to define it as a chance-constrained Markov decision process, where each of the states describe the locations that each of the robot has to travel, plus the energy consumption of the robots. Here are the examples of how the rendezvous can affect the total coverage or exploration of the system. On the left side, we have the actual trajectories that robots were supposed to visit, and we have the result of the rendezvous. So you can see that actual trajectories of the UAV performing the exploration have been increased because they have to choose new location to rendezvous in order to not have lose the power. Couple of things that we have noticed after the performing the simulation with this system was that if we are setting this user-defined low risk tolerance, we will have lower empirical failure, which is also intuitively possible to guess. And also UAVs, if we have lower risk tolerance, will actually meet more hope. The experimental setup for this is consisted of voxel drones and the ClearPath Jackal vehicle. The way that we are doing the communication between them is that UAV has to track the AR tags and understand that it has to land on it. At the moment, we don't have any other communication system between them. This is work in progress, and we're trying to import always larger, big demonstrations with multi-robot system. So that was a couple of ways that we can actually address the uncertainties. Now, let's talk about the underwater coverage. One thing that we have observed when we are doing experiments in underwater environments, that doing just simple bootstrapedic pattern that I have talked about on the first part of my presentation might not be feasible in the underwater environment. One, we for sure don't have any GPS information. Two, even if we have any state estimation algorithms, they are going to be failing most of the time. So how we can perform still some coverage of the environment, not relying on the state estimation and using minimal computation and minimal information from that environment. So one way that we have observed as a human when we are diving in an underwater environment, I don't have any information about my localization. I don't know where I'm located, but just looking on the current state, on the current image in front of me, I can understand how I can go around this object or shipwreck. So we did exactly that. We used that information to define the problem in the following way. We are given monocular image, the perception of the robot, and we do not rely on the state estimation. So how we can find a policy that will make sure that our underwater robot is following the shipwreck in a way that we are defining the following four motion primitives that we believe might in a combination help us to eventually perform complete coverage of this complex structures. One, we have to keep the shipwreck in the field of view, follow the shipwreck site, turn around the bow and stern of the ship, and circumnavigate the mast. We didn't have any available ready-to-use data, so we had to collect all of the data ourselves. We have built a stereo rig system in our lab that has the stereo configuration for the cameras. It has the IMU pressure sensor and internal computing power on the sensor. And we also used sonar to collect all the data. This is a handheld system. It's very similar to the underwater robot that you saw on the very first slide, but it does not have any actuation. But this is very handy to collect all the data, underwater data. And using this idea that I just described previously, that as a human, we know how to navigate around the complex structure, we wanted to do the behavior cloning for the robot. By that, what I mean, given the image of the current environment, we wanted to teach robot how it will change the yaw and pitch of robot in order to navigate towards these areas of the shipwreck. The way that we did it, we are given a user interface where the people will see the image and will assign classes to each of the changes of the yaw and pitch. And we use this neural network for training this classification problem, where the input is the current view of the field or shipwreck, and then the output is the values of the change of the yaw and pitch correspondingly. The data has been collected over the shipwrecks in Barbados, over Stavronikit and Palmer shipwrecks. There are only two shipwrecks that we collected data. We use both Aqua stereo rig sensor that I showed in the previous slide and the GoPro cameras. We have also used in simulation in Gazebo 4 shipwreck models from NOAA that we exported into Gazebo with Aqua robot. Our results have shown that we have 80% accuracy on the direction, on the prediction of the direction, when only we use simulation or only we use the real data. One of the reasons that we see this, that on a combined data we have low accuracy, is because the real world data and the simulation data that we had, they did not correspond to each other. And one way that we can actually resolve this problem is to have GAN-generated environments for the simulation that will have a much closer texture to the real-world environments. But our model was able to actually converge after only 500 epochs, and we have, yeah, it started working. So there is an example of execution of the trajectory of the aqua robot in the simulation mode. We have not been able to perform any demonstrations with this with the real system because this is exactly the time that the COVID has happened. So this was for the shipwreck, but what we did for specific environment, we have done training for the navigation system, right? But what if the information that we're interested is actually changing? What if it's not a shipwreck, but it's a coral reef or oyster reef, or maybe algae blooms? These are regions that we're interested to navigate over, right? And maybe we can do some different way that will actually reduce required training for just the control, right? And the intuition behind is that as a human, when I was using this behavior calling, one thing that I told robot is that there is a region I'm interested and there is a region that I'm not interested, right? So go towards the regions that I'm more interested. And I used also some depth information. How close are these regions? How far are they regions? How dense are these regions? So maybe we can extract that information and create some intermediate representation for each of these perception inputs. And we did exactly that. For any current frame, if we have some region of interest, we only need some segmentation network that will tell us that these are the classification of this area. So either that's oyster or it's a coral reef or anything that we're interested, right? Only one assumption that we're making here is that field of view has to be the same. It's either have to be top down, or if it's shipwreck type of areas, we have to go on that areas. And we can get the depth information from that image and build this intermediate representation of that environment that will strip down all the information about specific domain, whether that's oyster, coral, or any other thing, right? And then using that, we can now do the training step for the control policy. So now we remove that part that for every domain we're performing training, but we are only doing that for the intermediate representation. And with that, in the simulation, we have done this experiment where we are traversing over the oyster reef, and it shows that it's actually able to keep the oyster reef under its field of view. And to show that it's actually data invariant, what we did, instead of now oysters, we have used the classifier for the rocks. And now interest region is rather than oysters, but the rocks. And we were able to show that robot is still able to navigate over the rocks without colliding into them.
So in this one, you are still doing the movement of the robot, but based on the first estimate depth and then do it.
Yeah, so what we do in the first case, we were training on the raw image.
Mm-hmm.
So now we're saying that we don't need all that information about it. The only thing that we are interested is where interest regions are. That means you have classifier.
Mm-hmm.
And we want to know the spatial information, right? How close we are there obstacles or not? And that's depth information. So let's just use these two information, strip down all the domain specific things and give this to. So that will ensure that tomorrow, if someone comes to me and says that, you know, I also have similar field of view. Now we want to explore, for example, leaves in the environment, or we're interested to see how many cars are in the parking lot, right? So they still have top-down view, right? But they have classifier for me. If they give the classifier, I only need that information to give them the navigation method. Mm-hmm. But in the previous case, I had to collect all the data about the parking spots and do training, ask humans to annotate them, how they will move around it, and do the training on it.
But in this case, you assume you can compute the depth.
Yes. Yes.
Right?
Yeah.
So for that, either you need an extra sensor or you have the method to compute it.
Not ourselves, but there is an underwater package developed by our colleagues that they are doing underwater depth estimation, and it's also only using the camera information. Mm-hmm. So we're aiming to combine their depth estimation when we do real experiments with our method.
But in general, if you use just images directly, so that method. So if you just use images directly, that method works better or worse than if you use a depth map and segmentation?
It does not work worse because the annotation is same, right? But only the advantage that it gives you that you don't have to do that anymore.
You don't have to do what?
You don't have to use the image. Because what it ensures, right? That when we are doing on the image, the annotation, right? You always require that your navigation is going to be specific for that domain. But if we have this intermediate representation, that intermediate representation is working with anything. So anything, if it's coral, if you are giving the image, on the first case, I had to train on all the corals, on the raw image.
Yeah, but intermediate representation depend on something, which is specific to particular domain.
Yes.
So I don't see what's the advantage.
We don't do the training for each of the environments for the navigation.
But so you are expecting the depth map available through sensor
Yes.
and the segmentation. Are you using segmentation after here?
So yeah, we're using segmentation. So segmentation assumes that there is known classifier for this interest region.
Needs a training, right?
Yeah. So that's so in cases if you have existing classifier, for example, agricultural application, we were also discussing this today. For that, we have already existing packages that give you classifier readily, right? Maybe for underwater, we don't have specific classifier for some species or anything, right? For that, yes, you still have to do the training. But as long as you have classifier, you can use this method to do interest-based exploration. That's the advantage of this. Yes.
Thank you.
Thank you. Yeah, but that's exactly true. If you need to have the segmentation mask before.
And I assume that SLAM mapping doesn't work very well in this environment because every rock looks fairly similar to every other rock.
So in the simulation, it might even work, but in underwater real environment, it does not work well. There are packages. There is one package for underwater SLAM from my previous lab where I was a PhD. It works very well when you have good visibility underwater. In Caribbean, sometimes it will work if you are over large coral reefs where there are features. But the moment that you go over sand or you go to some areas that there are like the light is changing, there is a bit sun, it's going to fail. So the idea behind this is that how we can combine these global level plans, for example, having someone that is observing from above, boat, and have these local level plans with the underwater robot, right? That they don't have reliable state estimation and perform the collaborative navigation. Eventually, this is the idea that it's going to come down.
As we talk about during breakfast, so Megadari Pool,
Yeah.
University of Miami, he spent a lot of time on the underwater SLAM.
Yeah. He was actually interested. This is what we were I was talking about. He's interested in this work to extend that for something different, detecting something different.
Because he was postdoc of Burton Pond,
Yeah.
Classical SLAM structure.
Yeah. That's what we were in collaboration with Dr. Yanis Salimonos about this. But yeah, thank you for the questions. And this is just a few examples of the oyster reef environments that we compared with the boostrophic pattern and random walk patterns. The reason that we compare with the boostrophic pattern is because it's kind of state-of-the-art pattern for scientists. If they go somewhere to collect some data or even people that are doing the oyster harvesting, they will just do back and forth motions to collect some data. And if you don't know actual representation of the map, you can't really do exact boostrophic pattern, right? So you're going to do like some lawnmower motion. So given that, if we apply this both, how well we are performing, given that we don't have any information about the environment. And our experiments showed that our methods on average collects more data compared if they were to travel the same distances or using the methods that we have, they will collect more data. And so this work that I showed for this data environment is actually under review, and we'll know the results in a few days. But moving forward on this line of work, so this was environment that we have partial information about the environment, right? And by partial, I mean, even though it's unknown environment, the partial part is that we're assuming it's either oysters or corals or maybe shipwreck. So we have some inherent information about the environment. And as I already discussed it, moving forward, the idea is how we can combine this stateless SLAM-denied navigation with higher level pad plans that I presented for the multi-robot agents. And right now I'm leading these efforts for building this autonomous surface vehicle right now at the Maryland as well, replicating what we had at the University of South Carolina. We're making it to fit to ensure that single person will be able to deploy them without much overhead and be able to communicate on a surface level with the underwater vehicle as well. So with that, I give some motivation of some part of the small future work that I'm working. And coming back to this research dimensionality, my research is going to be expanding towards different aspects of it. Particularly, I'm going to move towards the unknown environment and try to ensure that the systems are, the solutions that we're providing are actually working on the full heterogeneous level. And this can be summarized as the vision that I have for my research, that I want to design scalable planning and coordination algorithms that are working for heterogeneous multi-robot systems that are able to work on the dynamic and uncertain environments. So this is the general picture of my research and how I'm planning to move forward. So I'm planning to combine the global navigation methods with the cooperative planners and the local navigation methods. I worked on each of these sites separately, and now the idea is how we can combine this and actually have working systems that will be collaboratively, efficiently collect data about the environment. To support my research, currently my research is supported by Army research grants and also USDA. I'm hoping to continue those collaborations. In addition, I'll be applying to NSF, NOAA, and ONR research grants. Currently, I have under review Martin Lockheed grant that will soon know the results. And there are 3 active grants from the Army Research Lab that we have and working at the moment for the cooperative heterogeneous multi-robot systems. For the collaborations, all this work will not be possible without collaborations. The nature of my research is interdisciplinary. And I'm hoping to work with the both computer science, ECE, and mechanical engineering departments. And additionally, because I'm interested in my research is grounded in the applications for the environmental monitoring, I'm hoping to also collaborate with National Center for Integrated Coastal Research at UCF. For the external academic collaborators, I have been very lucky to have great collaborators across different universities, and I'm currently working with many, particularly 4 research labs at the University of Maryland, and I'm hoping to extend that. I still work with my advisor at the University of South Carolina, my colleagues at the Dartmouth University, NOAA, and I hope to get collaborations at Nobel and extend all the connections. And eventually I want, as a new faculty and moving forward, I hope to also extend towards building relationships with the industry representatives as well. With that said, all this work that I presented would have not been possible without my collaborators, many great faculty and students that I have worked with. This is only part of the researchers that I have worked that I presented today, some of the works. So there are many more people that I have worked with, and the funding agencies that have funded my research. And also my acknowledgement to the UCF for inviting and for the AI initiative for having me today for the presentation. With that, these are some of the references of the particular papers that I have talked about. And with that said, thank you. And I'm happy to take any questions that you might have. Yes.
Do you have any opinion about the modeling of wave action? Because I've been told that one of the main reasons you can't just like take your standard like mobile, like ground vehicle, like planning algorithm and put it in the water is that the waves introduce a lot of angular uncertainty in the movement. So do you have some way of modeling that?
Yeah. I do not. The only way that we did that through the modeling of the current on the lake, but we did not do any data sampling from the oceans. But there is a research group at UPenn. Ani, she is working on this kind of problems at the GRASP lab, and she's actually trying to have the models of the environment, how they are affecting the motion of the robots. But that's not the field that I have done much work. But yeah, that's active research field and very important for the marine explorations.
So can your work can be applied to the space, like you're sending these robots to space and navigating? What would be a difference?
So the difference for the space, the offline algorithms can be used in the space as well. There are, of course, like fraction problems that you have to encounter, that the uncertainties that we're encountering in the space environment are related to the fraction. But if we have the air vehicles and ground vehicle communication, there's I'm not aware if there is a good communication between the vehicles, but that's another maybe uncertainty that should be taken into account. But the models that I have, I do not think, for example, an information-driven one will work in the space because the terrain that we have, for example, for the moon, right? It's kind of similar. So unless we have specific classification method that will tell you that maybe there are some areas that are interesting, I don't think we can directly apply the method that I have shown. But the global planning methods, of course, if you have data, if you know what is the environment, what the environment looks like, we can apply that to the space robotics as well.
Other questions? Okay, well, let's thank again our guest.
Thank you.
I forgot to mention yesterday from John Hawkins for the interested in the work. I think you've seen some of your StarCraft.
It was a good talk. Very nice.
Thank you, Brett. Thank you so much. Thanks for having me.
And his group is interested in for this game problem each other. He thinks it'll be simpler than StarCraft. And I guess his work is in
Oh, I'm not able to.
He's interested in actually like getting a lab card on this test bed. He wants to make the test bed into kind of a combination test bed. So I will send you the link to this work. It's on the